Hey, Ben Seaman is with us. Let's see, we've got Ben Harris and Ben Seaman. So we've got a class. Wonder why that's crooked. I wonder. Yeah, that's a little better. Maybe I could scoot this. Yeah, that's good. Hey, how about it, you two? Any questions for me?
Not that I can think of.
So did you say you're okay? Is that what you said?
Yeah, I'm doing pretty good.
Well, that's good.
How are
This,
you doing?
oh, terrific. Just doing just fine. This is the 17th of November. You realize in a month, this is all going to be over. Are you guys looking forward to that?
Always.
Yeah, it's going to be over. Okay. I think your I think your test is available. Let me look and see here. Today's the 17th. According to this, you're supposed to have your test available on chapter 6 and 7, and it's due Friday. So let me write that down. We've got an exam, to take home exam, open book. Isn't that nice? It should be available now. And it should be due Friday. This one doesn't write that good. Let me try a different one. We'll try this one. And what about, have you tried looking at that exam? Have you tried pulling it up yet? Probably not. But I think I make them available about 9 o'clock in the morning. This is the 17th, so yeah. There's a homework too. It's homework number 27. Yeah, I think so. Number 27. Homework number 27. It's 7:33, and it is due Friday also. That one writes a little better. That's pretty good. And then that's going to conclude Unit 3, and we start on Unit 4 on Thursday, which is Chapter 8. So we start on Chapter 8. On Thursday. That'll be fun. And there's just not much school left here, according to this. This says the final is on the 10th? No, on the 8th. Final exam is on the 8th. Okay, of December. Yeah. Well, let's see who's on board now. Let's see. We've got a good crowd. Braxton, Ben, Harris, Ben Seaman, Ashley, and Alex. I guess that's it for right now. Okay, class is going to start. Here's your last chance to say something or ask a question, then we'll start having fun. Well, you guys are awfully quiet. I want to go over some basics. I want to go over some basics. I want to go over a problem, review problem 7.5. That's what I want to do. And you know the first step on these problems is to draw a free body diagram. So let's do that first. All right. Let me find it first. This is review problem 7.5, I think is what I said. Where the heck is it? There it is. Okay, well, let's draw this to scale here. All right, it's 11 feet long. I'm tempted to use inches here. That'd be good. I wonder if I could. I wonder if there's enough room. All right, let's see. Well, there's the announcements. We'll try drawing this. Okay, we got 11 here. Yeah, there we go. And it looks like right in the middle, would that be 5.5? Something happens. And then something happens at 4. And something happens at 7. Okay. This is review problem 7.5. It's on page 411. And I thought it'd be fun to go over this because it hits a lot of the basics. Now, did I measure that right? 4 inches there, 4. Yeah, I did pretty good. 3 inches there, and not bad. Not too bad. Okay, now they have a distributed load there of 150. All right, well, here, let me draw that. Distributed load, okay. £150 per foot. Is that what it is? 150 pounds per foot? Boy, Jove, that's what it is. 150 pounds per foot. Okay, I'm going down. All right, and then they have a roller here at A. Okay, and a smooth pin at O, or is that D? That's D. I have to get some glasses one of these times, but not yet. And there's an 800-pound force right here. Let me get the red. Let me get my red color. There's an 800-pound force right here. Now we know there's going to be a force here at D, and there's going to be a force here at A. I don't know what to call them. How about FA and FD? Those are nice names.
Mr. Griffin,
Yeah,
is
I'm
it
listening.
800 or 8,000?
Ooh, we got our first thank you point of the morning, and it's a red one. That's special. Now, who was that just got that?
That was Alex.
Alex, appreciate your help very much, Alex, because I was going to get everything wrong and then wonder, well, what did I do this time? But thanks to Alex, we're going to get it right.
Mr. Griffin,
Yeah, I'm listening.
I think the exam tree is still not available in the Unit 3 section of Strength of Material.
You're saying something is available? Say that again, Mohammed.
I'm talking about the exam 3. I
No.
couldn't see it in the blackboard.
It's available?
No, it's not. It's not there.
It's not there.
Yeah.
Let me call my IT person. We're going to call the IT person here. It's so nice to have your very own IT person. La 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 la. Okay, we'll see if we can get her on the line here. Now, in the meantime, do I need to? Hey, IT person. Well, one of my excellent students says that exam 3 in strengths isn't available, and I thought it would be this morning. Okay, take your time. You guys are pretty smart. Are we forgetting anything here? I don't think so. Now they have a section here. This is section little a, and we'll get to that. But I tell you what, let's do. Let's put a red resultant force right here, don't you think? Let me get this red arrow here, and we're going to put it right here. Now you know that resultant force is the area of that distributed load. So I'm going to call on one of my excellent students. Oh, I know what I forgot. I didn't put down 4 feet here. 1.5 foot, 1.5 foot, and 4 feet. So this area, you can figure it. I don't want to spoil your fun. Let me call on somebody. And hey, thanks a lot, IT person. You're worth your weight in gold.
All right, bye.
Bye-bye. That's a great IT person. You know what? Can't beat it. Ben Seaman, unhook. No, that's not right. Unlodge. No. Unmute. That's it. Hey, Ben, unmute. And tell me, what's the value of this resultant of that distributed load? You tell me.
It would be 600 pounds.
Oh, that guy is sharp. He knows his stuff. It's 600 pounds. Good going. Okay, I think we're done with all the red stuff. And now the next job is we're going to do the, we're having a review, by the way. This is review problem 7.5. And we're just hitting some of the basic bonehead stuff that we're supposed to know. And the next thing we're going to do is we're going to do a shear loading diagram. We're going to do a shear loading diagram. And it'll go like this. Come on now. There we go. Now you all have that scribbled down on your papers there.
Yeah.
How about it? Why don't I shut up for 1 minute and give you a chance to draw the shear loading diagram. And then I'll draw it and we'll compare notes. Go for it. And then we'll draw the shear loading diagram. And then you know what we should do after that? What would really be fun is after we do the shear loading diagram, I think we should do the bending moment loading diagram. What do you think? I think that's a good idea, Mr. Griffin. Yeah, we're going to do both of them, but I'm going to give you a chance to. Did that show up? It's awfully faint. Let me make it darker here. Need to get a different pencil, I think. Not happy. Try this one. Still not doing good. Come on. Just not happy with these pencils. Okay, I'll give you another 30 seconds or so. See if you can't give a try on that shear loading. See, right now, we're trying to draw. Ooh, that one works. We're trying to draw the shear loading and bending moment loading diagram. Oh, wait a minute. Auga, I forgot something. We can't draw those diagrams right until we figure out these external forces. I skipped a step, didn't I? See, first you draw the free body diagram. Then you put in the external forces in red, and then you find the ones you don't know. Okay, well, let's do that. Well, we got to find, never mind drawing these diagrams unless you're way ahead of me. Some of you probably are by now. We got to find these forces. Here's what you could do. You could take the moments about A, for instance, and you would have minus 600 times 2 feet, right? And then you'd have minus 800 times 7 feet. And then you'd have plus F sub D times 11, right? 11 feet. Equals 0. Uh-oh, I ran out of room there. All right, help me do that. And we'll get our force at D there. Well, I got an answer. I wonder if this is what you got. I did something wrong. Let me do it again. Yeah, here's my problem. That's 8,000. It's not 800. I wrote it down as 800 again. But one of my excellent students helped me. They got a nice thank you point for it, but I don't remember which student it was. Isn't that awful? You do a good job and then nobody remembers you for it. Okay, I think I've got this F of D here. I got 5,200 pounds. And if you got 5,200 pounds, say uh-huh.
Uh-huh.
Yeah,
That's what I
there's
got.
one. Yeah, we're doing good. Now we're going to get to F of A. Now the way to do that is the sum of all the forces has to be 0. So let's see, you got 600 and 800 going down, 5,200 going up. And then you have this F of A. And see, that has to equal 0. Okay. Let me do that. Now, wait a minute. How come I keep writing 800? It's 8,000. When will I ever learn? You know, that's the bad thing about habits. They become ingrained and then you can't shake them. You got to replace them with a better habit, like maybe doing it right in the first place. Okay, well here, let me try this. 5,200 minus 600 minus 8,000. Did you get 3,400? F of A here, we think is 3,400 pounds. There we go. We got FA. Now we're equipped to do the shear loading diagram. And here's what it's going to look like. You're going to have a value here of 3,400. And because these are going down, you're going to have to subtract. We know what the area of this distributed load is. It's 600 pounds. So you're going to subtract 600 pounds. What's 600 from 3,400? Hang on a minute here. If you subtract 600 pounds, you get 2,800 maybe? Does that work? Boy, Jeff. I think it does. See, this here is 3,400. But it goes down to 2,800. Kind of takes a little, there you go. And this here is 2,800 pounds. And then what happens? Well, it stays the same. It stays the same. And it's flat till you get to here, and then it goes way down 8,000. So subtract just a minute. Subtract 8,000 from 2,800. Let me try that. I get minus 5,200. There we go. This is minus 5,200 pounds. See, this is 2,800 pounds. And boy, Joe, we're done. We've got our shear loading diagram now. Does yours look like that? I hope so. And now we're going to do the bending moment loading diagram. And how do you do that? Well, I think I've told you guys, you can just look at this and see there's nothing that's going to twist this thing here. That's just a roller. So you're going to have a 0 value there And you're going to have a 0 value there for your bending moment at both ends. And then you've got these lovely equations. You have one that goes like this. And one that goes like this. See what this says is that the shear is equal to the slope. Now, this shear is positive, so you've got to have a positive slope. So if it starts at 0, we got to have a positive slope. It's going positive. But you notice the shear gets smaller, so the slope has to get smaller. So I think it kind of goes like that. And see the slope gets smaller. And I can tell you how much it goes up. It's equal to this area. Well, what's the area? You see this trapezoid right here? Here, let me color it. Guys, what we're doing right now is we're having kind of a review of some basic important stuff here. See, the area underneath the shear graph is going to equal your delta M. Delta M. That area. Well, I can get the area of that. It's a trapezoid. And they taught me in school many years ago that the area of a trapezoid, see this trapezoid's kind of like that. It's equal to the sum of the heights divided by 2 times the base. Do you remember that for when you were in school, that the area of a trapezoid is the sum of the heights divided by 2 plus or multiplied by the base? Well, you see the base is 4 foot. And here's the heights. Okay, I'm going to add those up and divide by 2. All right, 3,400, let's see, 3,400, 2,800, divide by 2, okay. All right, I did that. I added the heights, divided by 2, now I'm going to multiply by 4. I got 12,400. This value of the bending moment right here should be 12.4 kip feet. I got 12,400, but we can give it that little extra pizzazz, call it 12.4 kip feet. And then see the slope's going to be constant at 20. See this, the slope of this graph is equal to the shear. The shear is constant in here, so it just goes, it's a positive amount. It's not 0. It's kind of, there, I tried to draw a straight line. There we go. See, it's a constant amount. And again, I can tell you how much it goes up. It's the area of that rectangle. Here, let me color that rectangle. We'll color it, let's color it blue. There we go. Does that show up blue on your picture there? Yeah, kind of. Well, you see that area there is equal to, it's equal to the change in your bending moment. Well, what's a rectangle that's 4 feet? It's 4 feet, right? Yeah, no, it's 3 feet. I didn't do this to scale very good, but see, that's 3 feet there. And the height is 2,800. So the area of a rectangle is the 3 times the 2,800. Let me do that. I got 8,400. So this thing goes up. You see, it was at 12.4, and it's going up 8,400. In other words, 8.4 kip feet, right? So that makes should be 20.8. This value right here should be 20.8 kip feet. That's your maximum bending moment, 20.8 kip feet, because I got to go back down to 0. And see here, the shear is negative. So that means the slope is negative. The slope goes down here. It's just a straight slope, straight down. There you go. Boy, Jove, we've got our bending moment loading diagram. Isn't that nice? We've got our shear loading diagram and our bending moment loading diagram. Now let's check it. This is called checking our work. It's a new concept I introduced a number of semesters ago to my students. It's called checking your work. What we're going to do is we're going to take the area underneath this shear diagram. See this here? The area, this is the area. We studied that in calculus. Remember, the integral is the area. You knew that. You see, we're going to take that area, and in this case, it's this green area here. I'll color this one green. See this green area here? That area is equal to the change in your bending moment. It's negative. I kind of lost my negative sign here. But I'll tell you what that area is. It's a rectangle. So you go base times height. Well, it's 4 foot this way. It's 4. See, it's 4 foot. And it goes down, what is that, negative 5,200? Is that what that, can I read my own writing? Yeah, 5,200. So if you have a rectangle and it's 5,200 by 4 foot, I'm going to multiply that. 5,200 times 4. I get 20,800. In other words, I get 20.8. When I do that, I get 20.8 kip feet. It has to go down. It's a negative because that's a negative. Well, if you're at 20.8 and you go down 20.8, boy, you're back to 0 again. That's called checking our work. It worked. I think we did it right. I think we have the bending moment loading diagram and the shear loading diagram. Yeah. And now that we have those, we could find the normal stress and the shear stress any place we wanted to. Here, let me show you the formulas. Let me make some room here. Do you have any questions about anything so far? Nobody said anything. Now here's where we're headed now. I don't need that stuff anymore. You all know there's homework, and my IT person put your exam on online for you. It's due Friday. You're going to do really good. We'll start chapter 8 next, well, on Thursday. Yeah, that'd be fun. And here's where we're headed. We can find the maximum normal stress, or any, not just the maximum, we can find the normal stress any old place we want to now. And we can find the shear stress any old place we want to. Now let me ask you some stuff. You guys are awfully quiet. Let me find here one of my excellent students and I'll ask you some stuff. How about my friend Ashley? Ashley, unmute and say hello, please, Ashley.
Hello.
Ashley, these important equations, they're so important because they tell us the stress. And you know stress is where it's at in this class. Ashley, tell the class the names of these important equations. What's the name of that one?
Flexure formula.
She's got it. What's the name of that one? Let me write down that name here. Ashley's right. This is the flexure formula. Very important equation. Gives you the normal stress.
Shear formula.
Yeah, good going, Ashley. Thank you, Ashley. That's the shear formula. And to find the normal stress, you got to know where this bending moment is. To find the shear stress, you got to know where this shear force is. Now, how do you find those? How do you find the bending moment? How do you find the shear force? You find them from these diagrams. You have to make the diagram. And from the diagram, you can find ultimately, you can find the stresses. See, it's stress that breaks things. You have to have the diagram. But we have a problem. Houston, we have a problem. We don't have this moment of inertia yet. We got to get that. Okay, well, look, here, I'm going to circle this. We got these. We feel pretty happy about those. But we need these moments of inertia here. All right, well, here we go. We're going to work on that now. Let me look at this and see here. Oh, gee, they've kind of got an upside down I-beam sort of affair there. All right, well, we're going to try our best here. Do I have room? I probably have room. Now we're going to have a 6-inch. I wonder if I could use inches. Why not? We'll do inches. That'd be good. You guys do your stuff to scale when you do it, don't you? Oh, of course we do, Mr. Cooper. Now let's see, what's the width of it? 1/2 inch is pretty skinny, isn't it? Yeah, pretty skinny. 1/2 inch, that's not very big. Not very big. Okay. Not very big. All right, and then we have a 2 inches. We got 2 inches up here. All right, well, we can do that. No problem. But now that's a little thicker. That's 75. That's 3/4 of an inch. That's a little bit thicker. Not much, but it's a little bit thicker. Yeah. And then what do we got down there? We got, did I do that right? 2 inches? Yeah, I did it right. And this is 4 inches. Okay, let's do 4 inches. Here, let's see. 4 inches will put us right here. There we go. Now we've got to find, hey, wait a minute. Before we can find the moment of inertia, we have to find the centroid. You know what? We're going over some really basic stuff here, aren't we? Well, let's see if we can find the centroid. Now here's the secret to finding the centroid. What you do is you put a red dot right here, put one right here, and you put one right here. That's how you have to start to find the centroid. And we'll measure the centroid from down here. This will be our y coordinate. I probably should write down this is 0.75 inches. And that piece in the middle is 6 inches. 0.75 inches. Two inches, 4 inches. But now this here is only 1/2 of an inch. It's just 1/2 an inch. Okay. Now what now? Oh yeah. We're gonna find the centroid. Here we go. You know the formula. All centroidal formulas look the same. Hey, do you notice in the numerator here, they have the sum of yi, ai. We learned the name of that. That has its own special name. Let me go to one of my excellent students here. Let's see. Alex. Hey, Alex, are you the one that got this honking big, thick, red thank you point a while ago?
That is correct.
Man, we appreciate you, Alex. But now this is a tough question. You probably won't get this. But I'm asking it anyway. Alex, you see this term right here in the numerator. It's got its own very special name. Alex, what's the name of that term there in that numerator? What is it?
Is it the first moment of area?
That's it. Boy, Jove, that's it. Good going, Alex.
Hey.
And see there, even a blind squirrel finds a nut now and then. How about it? I'm proud of you. Now look, that's what that Q thing is, Alex. Remember when we do this here? That Q, that's what that Q is. All right, well, great. Well, let's do it. Here we go. Well, I need this distance here. That little distance there, that's 1/2 of 0.75. That, you know what that is? That's 0.3. It's 0.375. 0.375. That's 1/2 of 0.75. Now I need this distance here. That's going to be 6.75. I think so. That's going to be 6.75. And then finally, I need this distance here, which will be, oh gee, it's 6 plus 0.75 plus 0.375. I'm getting 7.125 inches from the very, no, I need it all the way from the very bottom. There we go. From the very bottom up to there is 7.125. If you get lost, just speak up and I'll go back. All right, so here we go. We're going to go 0.375 times 0.75 times 4 plus 6.75.
Mr. Griffin,
Yeah,
shouldn't the middle one there be 3.75?
just a minute. Just a minute. You're absolutely right, and I was absolutely wrong. Now, who was it that just helped me then? Who was that?
Brian.
Brian?
Yep.
Brian gets a nice big honking thank you point. Good going, Brian. You're absolutely right. It's 3.75 times 0.5 times 6. Oh, gee, I ran out of room here. Oh, well, we can always tack on some more. It won't hurt anything. Plus 7.125 times 0.75 times 2. But we're not done yet. We got to divide by the area. Now, see, these are the areas here. So you got to divide by the area of each one. Now I'm going to shut up for a minute and a half or whatever it'll take. And I want you to plug all that stuff in. Man, that's a lot of trouble just to get that stinking centroid, you know what? They call this the centroid. Actually, it's a centroid of area because they also have centroids of volume. All right, go for it. I'm going to do it. You do it. Let's see what we get. Here we go. Now, does that say 3.75? Is that what it's? Yeah, that says 3.75. Yeah. Well, I got a centroid. I got the centroid is 3.075 inches. If you got that, say uh-huh.
Uh-huh.
There's two. I need a couple more uh-huhs.
That's what I got.
Okay. I think we got four more all of a sudden. Maybe one more.
Uh-huh.
Yeah, there's a I'll take I will. I'll take any day. Well, we think we have the centroid. Now let me mark it on here. Let's see. It's 3.75 up to that red dot. That red dot on mine kind of looks like a little Valentine, a little red Valentine deal there. So 3 would put you right about in here. We'll just put it right here. There you go. That's your centroid, and what it is up to here, up to the centroid. I'll make a little room here. It's 3.075. Now this inches. Now this is getting kind of messy, but that's all right. We'll be fine. That took a while just to get the centroid. Now, once you got the centroid, we're on our way to finding this moment of inertia I. So here, let's write the equation for that. Now this stuff is just tedious. It's like doing your income tax. It's kind of unpleasant, really. But we can do it. And can you see you can make a mistake here? Like I make mistakes all the time. Look at those thank you points. My students are smarter than I am. But you know, when you're dealing with something like this, you might want to double check it because money could be involved. Not only that, people's lives could depend on you getting this right. Okay, well, let's see. Here we go. Now to find this, we're going to need this distance. This is so messy, it's hard for me to draw it. But I'm going to need this distance here between the centroid of the whole piece and the centroid of the web. And I'll tell you what it is. It's 3.75 minus 3.075. That's what it is. And I can do that. I think it's 0.675. Do you think I might have done that right? Yeah, that's right. That distance there is 0.675 inches. We've got to have it. Hope that made sense. Now I need this distance here. From here to here. From the centroid of the whole piece to the centroid of this top flange. Now to get that, to the top flange is 7.125. And to the centroid, it's 3.075. So to get the distance from the centroid of the whole piece to the centroid of the top flange, it is I wonder if I did that right. 4050, you think? Boy, Jove, I think that's right. I think this distance here is 4.05 inches from the center of the whole piece to the centroid of the top flange. Lastly, we need this distance here. This distance from the centroid of the whole piece to the centroid of the bottom flange. We can do that. It's so important for you to draw your diagrams to scale. See, I measured that. I got my ruler out and I measured 6 inches. Ta-da. Look, 6 inches. See, I measured this thing. Do it to scale. Okay, now this distance here is, it's it's 3.075 minus the 0.375. I can do that. I know how to subtract. I get 0, 0. I get 2.7. That distance is 2.7 inches. 2.7. Now, after all that work, we're finally ready to figure out our moment of inertia. Okay, I need the room here. Now, where am I going to do it? Down here. Look at all this room we got. We don't need this anymore. We figured this out. We are going to write the equation. We're going to have to use the parallel axis theorem. And we're going to write the moment of inertia of the cross section of this beam. Now, why don't we start with this bottom flange? We're going to go 1/12, 4 inches times 0.75 inches cubed. But see, it's not, it's at a distance of 2.7 inches from where we want to be at, I think. Wait a minute, let me read this and see what we're supposed to do. I got lost. Determine the maximum shear stress. Oh, okay. All right, we can do that. The maximum shear stress is going to occur here at the centroid of the whole piece. I think I've told you guys that before. So what we want to do is we want to add the area of this bottom flange, which is 0.75 times 4 times 2.7 squared. We're not done yet. We got to do the web and the top flange. But we're going to find the moment of inertia about the whole piece, for the whole piece. And this is how you do it. Okay, let's do the web. The web is going to be 1/12, 1/2 of an inch times 6 inches cubed, right? Yeah. Plus 1/2 an inch times 6 inches times the 0.675 squared. Finally, we're going to do the top web. No, the top flange. Top flange, here we go, 1/12, 0.75 inches times no, 1/12, 2 inches times 0.75 inches cubed, plus the 2 inches, the 0.75 inches times 405 squared. Guys, I think that's it. It's ugly. Check it. If it's wrong, speak up. I need your help. But I think I did that right. That's the moment of inertia of this cross section of this beam. Okay, you got a minute and a half. Punch buttons and tell me what you get. I'm going to do it, you do it, and we'll see what we come up with. Here goes. Hey, Shane, unmute and tell me if you got that yet.
Yeah, I got 57.052.
That's exactly what I got, Shane. Holy cow. It's a miracle. Good going. So let me write the answer here. It's 57.052. Hey, Shane, what would be the units on that?
Inches to the fourth.
Yeah, good going. Inches to the fourth. Hey, we made a lot of progress here. Now, if anybody else got that, say, uh-huh.
Uh-huh.
Yeah, I get that.
There's 2 or 3. Yeah, great. Okay, well, now look at here, guys. We figured out this I now. It took us a while. This is not easy to do, is it? Now, what about this thickness thing? They want us to find, let me read it again here, what they want here, and we'll finish this problem off. They wanted the maximum shear stress acting at section AA. Well, at section AA, I know what the shear is 2,800. I know what that is, 2,800. I know what I is, it's a 57,052. Got that. Now the thickness is half of an inch.
0.5. Yeah.
That's how thick it is. Half of an inch. It's 0.5 inches thick. That's what that thickness is. So I know what that is. If I could only figure out this Q thing, that first moment of area thing, we could find the shear stress, the maximum shear stress at this cross-sectional AA here. We could do it. Okay, well let's find that Q thing. It won't hurt us any. There's a little room over here. Does it show up? Yeah, kind of. We're going to do the Q thing. And remember what it is. It's just the sum of the YIAI is what it amounts to. And do you remember the rules on how to do it? What you do is you draw a line. If you want the maximum shear stress, it'll occur here at the centroid. You draw a line through the centroid. I'm doing that now. And then you color everything above the line. Okay, well, let me do that. I'll get some color here. Here's some blue. This is what you do. You color everything. Ta-da! And I just colored everything above the line. There, that's what I did. And then what you do is you take the centroid of this blue piece, which would be right here, and the center of that one, that's already got a red dot on it. And what we need is this distance here. Gosh, this is complicated, you know it? That distance there, we can get, now let me think and think and think. Let me make some room here. Gotta have some room to write stuff. Going from here to here, I know what that is. It's 3075. Now coming all the way up to here, I think what that is 6.75. So here I'm going to take 6.75, and I'm going to subtract 3.075. And that should give me this distance from here to here. Let me do that. If I subtracted right, and I think I did, I just found that distance there. Now the area of that blue piece there would be the 3.675 times a half an inch. That'd be the area. But now what is this distance here? Well, that's the distance to the center of it. Well, you know what that would be? That'd be half of this 3.675. You'd have to divide it by 2. Yeah, by Jove. But now we're not done yet. We got to do this little top flange here. So I need a little room here. We know we're doing review problem 7.5. So what we'll do is we'll add to it the area of this little top flange, which is 2 times 0.75. 2 times 0.75, that's the area of it. So the area of this is that. But then we need the distance from here up to here. Okay, don't know what that is. But I tell you what it is. It's 7.125. Make some room here. 7.125 minus the 3.075, I think. I think that would give me the distance from here to that center, won't it? I think so, yeah. Okay, let me see what that is. That's a 5. You suppose I did that right? Yeah, I think so. So you have to multiply this by 405. You have to take this here and you add these and you'll get your Q. All right, do it. Let's see what you get. We're going to find Q. They call it the first moment of area. Well, I got an answer. I'm getting 9.4514 inches cubed. That's what Q is. If you got 9.4514, say uh-huh.
That's what I got.
There's 2 of us.
Uh-huh.
I think that was an uh-huh. That was another uh-huh. Now let me show you something kind of cool. You don't have to go above the line. You could go below the line. Here, let's do it below the line. I need some room. We don't need all this anymore. We figured that out. If you want to recover it, just watch the YouTube. We do need to keep this, though. That's the moment of inertia. This time, we're going to do it differently. We're going to color everything below the line. I don't think I've ever told you guys this. What I'm doing is I'm coloring everything I'm showing you another way to get Q. See, this is what we think Q is. We think Q is 9 point blah, blah. But there's another way. And really what we're doing is we're checking our work because it's got to come out the same. We can get Q by going below the line. Okay. Well, again, we need these dots here. Put a dot in there right in the middle of that little guy. And how big is that little piece there? Well, let's see. See, here's what we're doing. It's called the first moment of area, and I'm going to do these two areas. Now, this area here, gee, it's, oh gosh. I think I erased some valuable stuff there. It's 3 point, yeah, there it is, 3.075 minus the 0.75. Let me write that down. 3.075 minus the 0.75 gives you, I wonder if I did that right. Did I subtract correctly, you suppose? Yeah. I'm doing this area right here. That area is 2.325 inches long and 0.5 inches wide. But see, what we need the distance from the centroid of the whole thing to the center of that piece, which I think is 2.325 divided by 2. That makes sense. Now we got to do this bottom piece. You have to add to it, the area of that bottom piece is 4 inches times 0.75 inches. See, that's the area of it. And what's the distance from the centroid of the whole piece down to the center there? Well, it'd be, I think it'd be the same thing, wouldn't it? It'd be 3.075 minus the 0.75. It'd be the 2, I think it's a 2.325, wouldn't it? Did I do that right? I think so. Okay, I want you to take your calculators. And if we did this right, this should come out to be 9.4514. Try it. Try it and see what you get. Unless I made a mistake, which is definitely possible. I didn't get it. I did something wrong. Now let me see what I did wrong.
Professor Griffin, I think the one in the bottom, 2.325, should be 2.7.
I think you're right. I think you're right. It should be, you don't want to subtract this, you want to subtract, this is where I goofed up right here, guys. See here? I want to subtract, now who was that just spoke up? Who was that? I'm
This is
sorry,
Samuel.
who? Daniel? Samuel is on board, Samuel. You're one of the tres amigos. That was wrong. Samuel is absolutely right. It's 2.7, isn't it, Sam? Okay. Good going, Samuel. All right, now plug all that stuff in and see what you get. Here we go. I can't read my own writing. Is that a 2 or a 7? 2.3. Help me here. I'm starting to lose my mind here. 2.3.
It is a 2.
That's a
2.3.
2?
Yeah.
Okay. Oh, yeah, there it is. That's a 2 there. You're absolutely right. 2.325. Okay, here's what I'm getting. After doing all that, I'm getting Q is 9.4514 inches cubed. I got the same Q I got the last time. Hey, you know what? We just checked our work. We got the right Q, didn't we? It wasn't easy, though. It was not easy. Okay, now let's answer their question. They wanted to know what the maximum shear stress was at this section AA. Well, we got everything. Look here. We got all that stuff. We just need to plug it in. Let's do it. Here goes. I'm going to make some room, and then I'm going to plug all that stuff in. Now, the shear is 2,800 pounds. And the Q is 9.4514. And the I is 57.052. And the T is 0.5. Plug all that stuff in and we'll get the maximum shear stress. Go for it. Well, I wonder what you guys are coming up with. Let me. Let me do it again here. I'm not getting the answer in the back of the book. That's what's bothering me. Are you guys getting 927? 927?
That's what I got.
Okay. PSI, I think. And now in the back of the book, they have an answer for this. And they say, the book says 795. PSI. Book is usually right. And we only have about 3 minutes left for me to figure this out. This is R7-5. The book says 795 PSI. We got the shear right, 2800. I think we did that right. We got the Q, we checked it, we did it 2 ways. I like our moment of inertia. And the thickness is 1/2 inch, right? I think we did everything right. And I bet between the several of us, we're all getting this, so we probably did that together correctly. It should occur at the centroid, and we found the centroid. I was going to go ahead and find the maximum bending stress too, but we're stuck right now. I'm not getting the answer in the back of the book, and they're usually right. But you notice they have 2 answers. I'm on page 858. And they have 2 answers. They have a toss of B and a toss of C. Now, what are they talking about? I thought there was just one thing they were asking for. Does anybody have a clue? Toss of A and toss of B and toss of C. We're running out of time, guys. Anybody have any clue as to what on earth they're talking about? You can't have 2 answers. The maximum shear stress is not going to have 2 answers. There'll be 1 answer. There'll be a maximum. It can't have 2 answers.
Mr. Griffin,
Yes, I'm listening.
wouldn't the maximum shear be 5,200?
Where did you see the 52?
On our graph,
Oh,
like the negative 5,200?
yes. Yes, it would. But that's not at section AA. Didn't they want it at section AA? Read it. Find the maximum shear stress acting section AA. Well, that was an intelligent comment. But that's not the shear at section AA. That would be this shear in here. What if have you plugged that in to see what happens?
Yes.
You don't get the answer either, do you?
Well,
What do you get?
I'll find it. I got, let's see. I got 1,722.
Yeah, that's not what the answer. Guys, it's a mystery. I think we did everything right. I'm sorry we didn't get the answer in the back of the book. I
Mr.
think
Griffin,
there's a 50-50 chance here the book could be wrong. You know,
I
that
just looked it up on Chegg,
Yeah.
and it's the same. We got the same exact answer. It
Really?
It was 9. Yeah, it was 927.
Really? How about that? Well, bless your heart. It's sad, but our time is up and I got to go. I will see you. Have fun with that take-home exam. And I will see you on Tuesday, I guess, huh? Yeah. See you Tuesday at 9:30. Adios, amigos. The book is wrong. I'm gonna write that down. That I think we think that answer is wrong. That happens. It's pretty rare, but it does happen. Bye-bye, students.
Bye, have a good day.
Yeah, you do too. Take care.